In this video, I will show you how to use the second derivative test to find the open intervals on which this function is either concave upward, which is like this, or concave downward. And in past videos, we have learned that the way the second derivative test works, if the second derivative is positive, then that's where the function is going to be concave up. And if the second derivative is negative, that's when the function will be concave down. So of course, if we want to find the second derivative, we first have to find the first derivative. So that's what we're going to do right now. So we're going to do the derivative of f. So I think we're just going to have to use the quotient rule. So the quotient rule says we're going to start by doing the derivative of the top function. All right, this is going to be a fraction. So we'll do the derivative of the top, and so that'll be 2x. And then you multiply that by the bottom function, which you don't do anything to yet. So we're going to multiply that by x squared minus 4. And for the quotient rule, you put a subtraction here in the middle. All right, so now you switch it up. So we're going to do something similar, but this time we're going to leave the top function the same. So I'm going to have my x squared plus 1 unchanged. And the bottom function, I take the derivative. So that's why I'm going to have 2x. All right, so we take the derivative of the top, multiply it by the bottom, and then we take the top times the derivative of the bottom. And then in the denominator, we simply take the bottom function and we square that. So we're going to have x squared minus 4 squared. So let's simplify this down as far as we can. All right, so I'm just doing the distributive property here. So this is going to be 2x to the third power, okay, minus 8x. All right, and okay, so this negative x squared plus 1 times 2x, I'm going to take this 2x and put it in the front, if you don't mind. It just makes me feel better. And it's easier to show the distributive property. So keep in mind, I am multiplying by negative 2x when I do this. So that's why I'm going to have negative 2x to the third power minus 2x. All right, let's combine like terms in the numerator. Okay, oh, well, this is interesting. We have a 2x to the third power and then a negative 2x to the third power. So, of course, those are just going to cancel each other out completely. And then negative 8x and negative 2x is negative 10x. So we have negative 10x over x squared minus 4 squared. So that's it. This is the first derivative. So the second derivative will be the derivative of the derivative. So let's go ahead and work on that now. So we will find the second derivative. And again, we will use the quotient rule. So it's going to be the same type of deal. I think it might be slightly more tedious this time. But you start by taking the derivative of the top function, and that would just be negative 10. And then you multiply that by the bottom function unchanged. So I'm just going to multiply that by x squared minus 4 squared. And then subtraction. All right, next we take the top function unchanged. So I'm just going to have my negative 10x, and we multiply that times the derivative of the bottom function. So this is going to have to be the chain rule, so just emotionally prepare yourself for that, and slash make more space for that. So the outer function, I'm going to start by taking the derivative of the outer function, so that means the 2 is going to come in the front, and I'll have my x squared minus 4 still. So that's the derivative of the outer function, but then you have to multiply by the derivative of the inner function. All right, so the derivative of the inner function here will just be 2x. All right, so that's the top part of the quotient rule. And then you're just supposed to square the denominator. So of course, if I take x squared minus 4 squared and I square that, it'll be the same thing, but it'll be to the 4th power. Let's see, can I get rid of these? All right, so this is an expression for the second derivative. Obviously, we're just going to simplify this as much as we can. So I'm going to have f double prime is equal to, all right, what can I do? So for now, I'm noticing that we have x squared minus 4 here and here and here. I'm not going to change that. I'm not going to do anything to get rid of that because that's like a GCF that I'm going to be able to take out later. So I'm going to leave that alone, but I will simplify anything I can aside from that. For example, we have a minus negative here, so that's going to be a plus. Okay, and 10 times 2 is 20, times 2 is 40. And then we have the x and the x, so that'll be 40x squared. All right, x squared minus 4. Okay, so we have x squared minus 4 to the 4th power. Notice that every single term has one of these guys. All right, every single term has one. So what I can do is I can cancel out one of each of these. Technically, I guess you could say I'm taking this as a GCF and putting an x squared minus 4 out in the front. Okay, and that would leave like negative 10, and now there's going to be one less. Okay, and then I'm canceling it out, but I think you get it. I can cancel out one from each of these. So that's going to leave me with f double prime is equal to negative 10. All right, so I've canceled out one of these, so it's going to be just x squared minus 4 now. There's only one left. This one only had one to begin with, so if I cancel out one of these, it's just going to be gone, and I'll just have the 40x squared. And I'm canceling out one of these, so that'll be x squared minus 4 to the 3rd power. Okay, so now I guess I will go ahead and do the distributive property now that I've canceled out my GCF from all terms. So I'll do the distributive property. So I'm going to have f double prime is equal to negative 10x squared plus 40 plus 40x squared. All right, the denominator will be left alone. Okay, combining like terms, that's going to be 30x squared. So I'll have f double prime I don't think I needed a fraction that big, but whatever. So I'm going to have 30x squared plus 40. Okay, over x squared minus 4 cubed. All right, this is a little bit of a long problem, but we're almost done. Okay, I'm going to have to evaluate later, so it makes it easier if I take out the GCF of 10. So this would be 10 times 3x squared plus 4. All right, just makes it a bit easier to evaluate later. Over x squared minus 4 cubed. All right, we did it. This is the second derivative. Now we are ready to use the second derivative test, okay, which involves, like a number line and stuff. Okay, how much space am I going to need? I probably don't need that much. All right, I think I'll just, sometimes I go ahead and do the first derivative test just for fun, but this problem was sufficiently tedious that I think I'm just going to stick to the second derivative test only. Okay, you know what? First we need to find the critical numbers here. There's one thing we need to keep in mind before we find the critical numbers. Normally when I go for the critical numbers, I'm asking myself, where is the second derivative equal to 0? And then I ask myself, where is the second derivative undefined? All right, these are the two sources of critical numbers. However, there's always something that we have to ask ourselves first, and that is, way back at the beginning, are there any values at which the original function is undefined? And we see this denominator here, so we know that x squared minus 4 cannot equal 0. You can't divide by 0. So, okay, f of x is undefined, where x squared minus 4 is equal to 0, okay, because that would cause the denominator to equal 0. And if you solve this, and we could either do the difference of two squares, right, x plus 2 times x minus 2, or I could have added 4 and taken the square root. Either way, you're going to get plus or minus 2. So x equals negative 2, I'm using the zero product property, x equals positive 2. These are two places where the original function is undefined. So these are going to be asymptotes. So keep this in mind. We have asymptotes at negative 2 and positive 2. So this supersedes anything else that happens. So if we get some critical numbers down here, if any of them are positive 2 or negative 2, we will have to say, well, we already know there are asymptotes there, so nothing new will happen. So anyway, back to the question. Where is second derivative equal to 0? A fraction can only equal 0 when the numerator equals 0. So this question is equivalent to 10 times 3x squared plus 4 equals 0. All right, the second derivative will only equal 0 where the numerator equals 0. The denominator can't be 0, so only the numerator can be 0. Dividing both sides by 10, I quickly get 3x squared plus 4 is equal to 0. My spidey sense is tingling. Do you see what's about to happen? Let's do another step. If I subtract 4 from both sides, I have 3x squared is equal to negative 4. Doesn't this seem impossible to you? when you square something, it's always going to be positive, and you're multiplying by a positive number. There's no way you're going to get a negative number out of this. You know, you could go a couple more steps if you really wanted to. X squared is equal to negative 4 over 3, for example. You can't square something and get a negative number. Or if you take the square root, you're going to get an imaginary number. Either way you want to look at it, there's no real solution here. Okay, so no critical numbers. All right, so let's move on to where is the second derivative undefined? Well, this will be undefined where the denominator is equal to 0, similar to what we just did with the original function. So x squared minus 4 cubed equals 0. This will show us where the function is undefined. If we take the cube root of both sides, then I will have x squared minus 4 is equal to 0. Does this seem familiar to you? This is exactly what we had for the original function. So you can see I'm going to get x squared equals 4, take the square root, x is equal to plus or minus 2. But that's the same thing we got. These were the asymptotes. All right, these values are undefined for the original function. So nothing new is going to happen here. So I'm just going to say these are asymptotes. All right, these are asymptotes already. Okay, the function is undefined at those values already, so nothing new is going to happen there. So, okay, when we do our second derivative test, when we make our number line, we're just going to use the asymptotes. All right, maybe I better leave them clearly visible though. Okay, we'll just use our asymptotes here to split up the number line. So here we go. Here's my number line. Okay, I'm going to have my negative 2 and my positive 2. I think it's good to keep in mind that these are asymptotes, so I'm just going to put some dotted lines here to remind us that, you know, these aren't going to be inflection points or anything like that. They're just asymptotes. All right, so remember we are doing the second derivative test, so we need to keep in mind what the second derivative is. But here come the test values. Okay, and this is the second derivative test, so I'm just going to mark that down here somewhere. All right, we're doing second derivative. So we'll use test values of negative 3 and 0 would be good. Okay, we'll use 0. And we'll use positive 3. Okay, those will be our test values. Okay, so let's start with negative 3. So how did that thing go again? All right, so we have 10 times 3x squared plus 4. So we're going to have 10 times 3 times negative 3 squared plus 4 over, okay, x squared minus 4 cubed. Okay, so we're going to have negative 3 squared minus 4 cubed. All right, so now I can stop scrolling up all the time. So what's going to happen? So I'm going to have 10 times negative 3 squared is 9. 9 times 3 is 27. So I'm going to have 27 plus 4 in the numerator there. Down here I'm going to have 9 minus 4 cubed. 9 minus 4 cubed. All right, so let's talk about where the function is positive and negative. So in the numerator, everything is positive. So I'm going to have a positive numerator. In the denominator, 9 minus 4 is 5. That's positive. Okay, so that means we're dealing with a positive situation. And when the second derivative is positive, that tells you that the function is concave up in that interval. So it's going to be concave up in here. So 0 should be easier. Okay, I'll just use this as a model. So if we substitute in 0, then I'm going to have 10 times 3 times 0 squared plus 4 over 0 squared minus 4 cubed. All right, well, the term here with the 0, that's gone. So that's just going to be 10 times 4, which is 40 in the numerator. This term is gone, so this will be negative 4 cubed. So that's going to be negative 64. So yeah, remember, when you raise a negative number to an odd power, it stays negative. Okay, so we have a positive divided by a negative. So that is going to be a negative, folks. And when the second derivative is negative, that means the function is concave down in that interval. All right. Now the last one is going to be kind of fun in the sense that we're using 3. Notice that we used negative 3 the last time. But notice that everywhere we have a negative 3, we have an even power. So we have this negative 3, but it's an even power, so that turns it positive. We have a negative 3 here, but it has an even power on it. That's going to turn it positive. So it doesn't make a difference whether this is a negative 3 or a positive 3. You're going to get the same answer. So we really don't have to redo that calculation. We can just immediately say, well, it's going to be the same result. So it's going to be positive, and the function will be concave up in this interval. So that is enough for us to go ahead and answer the question. We were looking for the intervals where the function is concave up and the intervals where the function is concave down. Okay, so concave up from negative infinity to negative 2. All right, negative infinity to negative 2. And also concave up, so union 2 to positive infinity. And there's one interval that is concave down, and that is from negative 2 to positive 2. All right, let's wrap up this video with a quick peek at the actual graph. So as predicted, you can see the asymptotes here at negative 2 and positive 2. And as predicted, the function is concave up from negative infinity to negative 2, concave down from negative 2 to positive 2, and concave up from 2 to infinity.